Hello and welcome everyone to this webinar hosted by Toradex. The title of the webinar is Unlock the Power of Embedded Computer Vision, a deep dive into optics, sensors, and image processing. So hopefully you are in the right webinar. So my name is Carlos Gonzalez. I am the head of partnerships at Toradex, and today we will hear from Artyom Stalaryuk, who is an image vision expert at DAB Embedded. He will walk us through very insightful content. We are also accompanied today by my colleague Bruno Mello, who is from our technical success team. He has a lot of experience with the vision technology at Toradex.
Hello, everyone.
So just before we jump and we dive into the webinar, let me cover a couple of housekeeping points. So the first one is to use the chat window of the webinar tool if you have any technical issues. We'll jump in and try to help you. Second one is to use also the chat window to type your questions in the chat in case you have any questions for us. We will not be able to answer the questions right away in the webinar, but we'll go through them at the end of the session during the questions and answers time. The webinar will be recorded and it will be made available on demand in about a week from now. With this, let's get started. So please, Art, please take it from here. Thank you so much.
Thank you, Carlos. Good afternoon, everyone. We will present today some interesting things about the cameras. Grab a cup of coffee or tea. Let's start with that. So I will present myself. So I'm a CEO of the company here in Belgium that produces the cameras, and together with the Toradex, we want to bring you some more interesting things about the cameras and how it works and so on. And thank you very much for Toradex for hosting this. Today we will speak about in general about lenses, sensors, interfaces, some ISP aspects, how data processed, and output formats of the sensors, and the specific things about the TI implementation and Aquila board. And then we will have a discussion where you can ask questions. Quickly about our company, we are a producer and here in Belgium, the camera heads from VGA resolution to 20 megapixels. We together with edge processing platforms and frame grabbers, so we are providing full set of products to get images and process using AI and machine vision stuff. We are covering use cases like segmentation, object detection, and so on, and we are creating a full pipeline to get a video, process video, and store or record or transmit. And we are working with a number of customers in different areas. It can be object detection and warehouse, inventory. We're working with the shops, retail markets to create the cameras and AI for retail and people counting using standard RGB cameras and also iToF. Starting from the discussion that we're gonna do today, I would like to start from the point that we have separating the cameras on three big piles. The first of all, this very small, tiny modules, camera modules that are available on the market. It's mostly mobile sensors. They can be color or monochrome with MIPI, DVP, or SPI interfaces, but they're very small. I put 8 by 8 millimeters, but it can be even smaller. It can be 6 by 6 or 4 by 4 millimeters. The benefit of it, it's a small, it can include lens system. It can be 5, 6 lenses, I will show you later. It includes also autofocus system, coil motor, but you pay by size of the pixel and also by the SNR on certain moments. Then next, a type of sensors, sensor modules, it's kind of middle class, I call this. It's a kind of maybe 15 by 15, 17 by 17 millimeters. Includes sensor, small FPC, and also M12 lens, or at least lens holder, and can be with or without IR filter. And also we can talk about the full-size modules. They can be with the big sensors, huge pixel sizes, and it brings us a high speed, good SNR value. It requires external lens, external filters, and brings a number of additional interfaces like SLV, SAC, LVDS, or sub-LVDS, and so on. I would like to open a poll and ask you questions about what kind of sensors, if you have experience with the sensors in the past, or you're going to use at the moment, or you want to start a project, or you just want to hear about what kind of things can be done with the sensor, but we're not going to use. That's kind of like 5-10 seconds, and we can discuss about that. Okay, I hope you done. Okay, that's quite interesting, because I see you are using at the moment, so you probably find something interesting in our slides. Thank you. We can go back to the slides. We can close the results. If we're talking about mobile sensors, they're quite small. They're really packed. They can, as you see in the picture, they contain a number of lenses, maybe 5 or 6 types of lenses, IR filter, sensor itself, and also a board, small PC that contains all necessary components like maybe decoupling capacitors, EEPROM for calibration, and also might be power supply units, depends on the sensor implementation. You can normally order or design by yourself, or buy on a free market what exactly needs. And also this kind of sensor contains what is called motor for autofocus. It's not means autofocus out of the box, but you can move lens group back and forth. Let's discuss about lenses. So we commonly use of three types of lenses, like M12, CS, or C-mount lenses, large lenses, and very specific telecentric lens. Telecentric is mostly used if you want to move your object and keep the same shape of the object independently of the distance to the object. While if you use M12 or the other lenses, you will see the object is changing his shape. It became smaller or bigger, depends on the distance. Difference between CCS, you can see that it's only in focal point distance from the thread. The thread is the same, but focal distance is different. So be careful when you're selecting right lens for your application. It might be important. In the datasheet of the module or of your camera system, you can see the FFL value. So this is a value exactly between the thread and focal point. Another important thing is that we're talking mostly about lenses, but how this lens projects the images on a sensor. On the left side, you can see a typical projection of the image on a sensor when we're talking about not a big angles. On the right side, on circular frame, it's typical for fisheye lenses when the angles is quite big. So when you select the right sensor, be aware about this. Next thing is about the focus distance and aperture. So when we are selecting right lens, we need to also think about aperture size, because depends on aperture, you will receive more and less light, but you also pay depth of the field. Less aperture, you have a bigger depth of the field, but it's a dark image will be dark. You probably need to play with exposure time or gain. If you have a large aperture, you pay with short of depth of field, but you will get a lot of light. That will be a bright picture. Another important point, yeah, there is a quick explanation how it works. So you have, if we reduce the aperture, depth of field increasing. Another point that we need to know about lens is a field of view. Typically, you need to measure your area and you need to select the right sensor, because it depends of the pixel size, focal length. You can calculate size of the area and the field of view. So you need to select right diagonal, horizontal, and vertical field of view. You have here I bring the formulas. You can check that later, but this is quite easy to calculate. Then what we have, what kind of issues we have out of the optics. So first issue is a chromatic aberration. It's really nasty when you have a really strong front light. You will see red and blue shapes of the on the edges, especially on the contrast edges. But we can eliminate that. There is two ways how to do that. So we can use more complicated lens using a chromatoplet, or do the ISP tuning, or both. So if you use both, that will be definitely much better than one another solution. Then another thing is lens shading. It's a really annoying thing, but it's available. There is two types of lens shading available. One of the lens on the light side, on the left side, you can see luma shading. It's only it becomes brighter in the center and darker in the corners, but in a color shading, it's also shifting in the spectrum. So you really need to do some ISP tuning to avoid the color shading. But it's a static and doesn't depend on the scene too much. Another distortion is it's another thing is of the lens is a distortion of the lens. So we, especially if you're talking about fisheye lens and big angle lenses, we have and you see in the left picture, it's a quite heavy distortion. So we need to use a lens correction module in an ISP to undistort the images. Type of distortions we know four. So we kind of, no distortion is quite a small field of view, so small angle, sorry. Then we have barrel distortion, concussion, and mustache distortion. Typically, ISP has the engine that able to do the polynomial distortion model or fisheye distortion model. And when we do the calibration of the lens, we provide a coefficient, and we select right model, and we provide a coefficients to the unit, and unit will do a job for us. For every frame, it will reconstruct the image. Another thing is vignetting. We have on the left side, it's quite similar to the lens shading, but it's more about and we will see on depending on a scene. Sometimes it can be quite heavy vignetting. So again, the corners became darker, centers a bit brighter. That can be fixed by ISP also. So we need to calibrate that. Last but not least, this is a flare. Flare is a bit nasty thing related to the strong sunlight or light source that comes from a site. We can fix that by using a hood or blend. So you need to have some kind of protection from the site that on sun or light cannot come from specific angles. I would like to run another poll and ask you what about your application. If you can bring a quickly overview about your application, will be great. Let's have again 10 seconds. Okay, thank you very much. Let's see. Okay, nice. So I see that mostly is in industrial machine vision. Great. Then we have something to speak about that. Thank you. Let's talk about sensor types. So we will talk today about CMOS, but I will just bring you a list of another types that are available today in the market. So we have kind of popular spot sensors, time of flight, event-based, multispectrum sensors, SWIR, and ultraviolet. Other less popular. About CMOS sensors. So if you look on a CMOS sensor structure, we have microlens array, and then we have a color filter array. It depends, of course, if you're talking about monochrome, there is no color filter array. Then we have a layer of photodiodes, pixel transistors that grab the charge, and bonding layer that distributes signals to the ASIC level. If you're talking about pixel array, today we are more and more using back illuminated CMOS sensor. But some while ago we was using front illuminated. But if you compare, back illuminated has we're using front layer that receives the light, and photodiode locates on the front. It brings more sensitivity, higher speed, and lower noise. About ADC structure, there is two general parts of sensors available. One of them have only one or double ADC input that grabs pixel by pixel, row by row. Then we have column and ADC. So we have ADC per column. If you look on the structure, typical rolling shutter or global shutter uses these ways of getting data through the ADC. So you see, for example, in conventional sensors, we have one ADC and, of course, some block for noise reduction. But on the right side, you see the implementation is much better in terms of high speed and low noise system that allows us to use ADC per column. And then if we compare with a global shutter sensor, global shutter has the same column-based receiver ADC part, and it has also pixel memory. After the pixel array, we have a digital logic. Digital logic allows us to receive the data from ADC, process, doing some post-processing. Some of the sensor depends on complexity, has the white balancing block, auto exposure block, black level correction block. Typically, a sensor has also a text pattern generator, especially used if you want to test your interface. You're not sure if this interface is working fine and so on. Test pattern generator used for that. We use also, there is a timer generator, allows us to synchronize camera with other cameras or host processor, and also provide timings for the ADC and readout block. Some automotive sensor has a safety features. There's also a part of the digital logic block. Talking about issues, first thing we need to take into account if working with a dark environment, it's dark noise. Dark noise is available when you turn on a maximal highest gain. It will not be a black picture, it will be some noisy on how you see on the left side. But depending on a sensor, if your sensor has a really good dynamic range, you probably can see even a really low light, you can see the difference. On the right picture, you can see using special algorithms, you even can extract the data or symbols or text or QR code, whatever. So this is a quite important characteristics of the sensor. Sensor also has a pixel non-uniformity. Means that we cannot manufacture every pixel in the same way as a previous one. So let me say that, we have some noise from the pixel, but this kind of noise is the same from frame to frame, so we can subtract. Most of the sensors has this feature already on the board, so you don't need to take care about this. It's already subtracted, and you will get a nice picture out of it. Another thing is static pixel correction and the back pixels. Of course, it's the same story as with the displays. There is during the production, manufacturer cannot produce a sensor 100% correct in terms of pixel structure. Might be bad pixels. Bad pixels, I mean, they not might react on the light, or they changing their color depends on the light and not correct color, and bad behavior. And for that, manufacturer of the sensor has a special table that you can provide data how to fix that pixel, what to do with that. There's two ways how you can fix that, using sensor static pixel correction, if the sensor provides that ability, or using ISP. We will talk about that later. There is some kind of similarity to ISO available from a CMOS sensor. If we're talking about gain amplification, it's not exactly, but something we can say if we can see correlation between analog amplifier and ISO level. There is also important thing that need to be careful when you're working with machine vision, especially when you're using light. We need to be careful with the way how what kind of light we use, angles, number of light points, and how it's implemented. So be careful when you select right light source. You can, of course, experiment, but this is also an important point. If you see already kind of high noise on your camera, probably you need to use a light source. I just wants to ask, what do you think? Do you need a light source in your project, or you think it will be fine to just use whatever in ambient source or whatever? Let's see. Okay. Thank you very much. Okay, great. That we then they have something to discuss about that. Thank you for the poll. About sensor features itself. So we already discussed about global shutter, rolling shutter, but why? What is the difference? The difference is how sensor read out the data from the pixel array. The global shutter logs the energy in every pixel memory and then read out without time delay. Rolling shutter is reading line by line, while you will definitely see motion blur. So then we need to carefully select sensor per application. So global shutter is mostly for high-speed applications, rolling shutter more for static scenes, low-speed applications. So be aware about this difference. But selecting rolling shutter and global shutter is not only about sensor, it's about lighting. So especially when you want to use laser or VCSEL laser, and we come to the fact that we need to be careful, especially about eye safety. Because you see on the left side of that picture, global shutter shows that flash duration can be quite short because we have exposure time single for all the lines. Speaking about rolling shutter sensor, we need to create a really long period of lighting to get the correct flash duration and to get a nice picture. So maybe it's not efficient, or you will see flash bands. Another thing is HDR. HDR is really nice stuff, especially today. A lot of sensors providing this feature. This feature allows you to get nice and contrast pictures, especially when there is not enough light, or you have, like on this picture, you have a tonal or with a strong different contrast aspects. I advise you, if you have this feature in the sensor, try to use that. Only one thing you need to know about this feature: you will lose frame rate, of course, because we are having two frames with two exposure times, one with a high exposure time, one with a low exposure time. So we need to process later in ISP these two frames, or sometimes sensor able to make 3 frames in the same time, not at the same time, but one by one. So we will lose FPS definitely, but we will increase dynamic range. So if we look on another technology that Sony presenting today, they have technology allow us to not lose FPS by using different gains. So they take the same picture, but with the 3 types of gains. Another interesting feature that Sony on Semi or other on Omnivision provides is LFM, LED flicker mitigation technology. Especially it's in automotive domain, but you might find this interesting for your application also. This technology allows us to mitigate the issue with the LED dashboards or signs when they're flickering because of the refresh rate, especially when your sensor is running on 120 FPS or kind of like this. About subsampling and binning, so you can reduce resolution of your sensor. For example, you have 8 megapixel. You can reduce your resolution 2 times row and column in 2 ways. You can increase your dynamic range, then we call that binning, when then neighbor pixels will be energy collected in a single pixel. Or we do subsampling, when we're not using these pixels, we just lose information from that pixels by reducing. Depends on application, you can choose which way is important. But frame structure, typical frames that we receive from the sensor, here example of MIPI bus, but can be DVI or other interfaces. The frame contains several interesting features, like maybe frame start from frame end data type, and then we have a number of lines specific to your sensor, like embedded data, or maybe the black level, black pixels for later for black level calibration. So if you look on a frame, you can might find something interesting, what kind of information you need to get this from the frame structure. Speaking about metadata that I showed you one slide before, metadata can be interesting if you need to know what's happening from frame to frame, because sensors sometimes do changing, for example, frame sizes from frame to frame or to ROI. You probably need to know your frame size, gain value, current Vmax, Hmax values, black level value or temperature value, and also data type that you receive. If we're talking about gain control, we have 2 or 3 types of gains. Another gain is a gain gain amplifier that works before ADC, so we can tune the gain of that amplifier. Its amplification is quite good because it is not to impact on a noise, mostly not, and also retains dynamic range. On digital side, it amplifies, of course, noise and signal, and then reduced in dynamic range. On the digital side, we can have 2 or 3 gains because of the HDR frames. So be aware, please, when you're designing driver, for example, of the sensor. And also, these gains can be adjusted by ISP. Talking about exposure control, it's another control that allows us to make scene brighter, let me say, and collect energy from the light. But exposure time can impact on FPS. So be careful when you create a long exposure time. It might be this thing that impacts on your thing. And of course, exposure control depends on a global shutter or rolling shutter. Thinking about sensors, that we can say that we able to change on a modern sensors, we can change the ROI zone. We can create a ROI zone, and we can do kind of cropping with that. And also, some of the sensors provide you a way to zoom out in a sensor level itself. So really, can you provide zoom aspect, and sensor can do the downscaled images. So you can it can reduce the bandwidth, but at the same time you can use on the one frame you can see full image, and then you can zoom in. Or for example, you run full HD instead of 12 megapixel resolution, you run full HD mode, and then you can move your window inside of the 12 megapixel resolution, and also zoom in to create to see the full picture, but it will be downscaled to full HD. There is also a feature that sensor provides. It's a multi-ROI, means that you can select 5, 4, 3 zones instead of full frame. You can select the small zones, and from frame to frame you can move these zones or change the size of these zones. Normally, every ROI frame comes with a metadata, so you know the size of the frame, you know the current statistics of the frame, and also benefit of that, you can reduce the bandwidth of your bus and processing unit. Another thing that we need to discuss is about camera synchronization. Typical cameras, typical sensors has the external exposure trigger, external synchronization trigger allows us to synchronize all the cameras, and also control exposure time. So while you keep the trigger, exposure time can be changed. And also some of the sensors provide you ability to control the light source. So while exposure time is there is a strobe for the flashlight, so you can control your LED or VCSELs laser. Then talking about multi-camera solution, you can really drive a bunch of sensors, for example, with various number of lenses. with the same sensor, the group of sensors with number of lenses. So one of the sensor can be master sensor, all other sensors can be slave. So one sensor sends the sync signal for all of them. And then you can use the video MOOCs to select which sensor you want to stream right now to the ISP block. Or ISP can be a master master trigger for your slave sensors. So depends on the scheme, but this is a possibility. Talking about the kind of pixel array structure. So we have several options how this can be done. So we have color sensor that has a Bayer pattern mask. There is a 4 subtypes of the Bayer pattern. As you see on the picture, you will receive not really RGB picture, but you will receive this picture with a lot of green pixels. That's why we call that engine that in ISP that does the job for us. It calls debayer, so demosaic, that does the mosaic for us. Another type of demosaic of the pixel structure Sony presented called quad Bayer. It's the single color filter, but there is a 4 photodiodes. It's increased dynamic range and especially used for mobile sensors. And they also, on a chip level, they do remosaic for us, so we can receive standard Bayer pattern. Another pattern is RGB-IR. This pattern allows us to receive, after the ISP processing unit, IR picture and RGB. And actually, this TI processor supports that, so we can have 2 pictures in the same time. And it brings more higher dynamic range because IR part can improve the quality of the RGB sensor. And especially we can reduce motion blur when we're using both pictures because it shoots in the same time. Monochrome sensor is a bit more simple. There is no Bayer pattern mask, no color filters, so you can skip number of blocks in ISP. About sensors interfaces. So we typically use 2 types of sensor interfaces between processor and sensor itself. It's DVP or MIPI CSI2. But there is, of course, a number of interfaces that are available for machine vision applications, but we will speak here about mostly these 2. So DVP is a bit slower. It's a parallel bus with external signals for synchronization. CSI2 DPHY allows us to transmit high band data rates up to 2.5 gigabit per second, and TI using this interface. And also this CPHY interface is also a MIPI standard interface, but allows us to transmit much higher rates and also use instead of a dedicated clock lane, there's an embedded clock in the data lanes. Besides of that interfaces, we have a number of other interfaces like SLTS AC, High SPI. They are both proprietary, and one of the Sony, second one is onsemi. SPI, there's a simple SPI and an LVDS interface. Currently in our world, let's say we were using, if we need a long distance between sensor and processing platform, no matter why, we are using different types of technologies like GMSL or FPD-Link. It allows us to transmit data between the camera head and processing unit up to 20 meter, and also provide a power for the camera module. So as you see on the picture, we have serializer unit, deserializer unit, and between them just coax cable, and that's it. It also reduces a number of problems like AMI, compliance, and so on. These interfaces have really low latency. There is not like 10 milliseconds. No, it's really low latency interfaces. About sensor format output. So typically sensor, if you're talking about color sensors, they are providing raw outputs, but they are providing actually Bayer outputs on top of the raw format. If sensor has ISP on the board, so can do UV output, RGB or JPEG. For monochrome sensors, can be raw or just Luma outputs. Without talking about ISP and processing, the ISP, the camera ISP and a video on a processor, video processor side is quite complicated stuff, because it may be 30, 40 stages to process all the data from the beginning to the end to get nice and clear picture let's say to reduce all the impact from the lenses, from light and so on. And if we looked on the results, on the left side, I put a picture from a sensor that has the ISP block, the very simple ISP, like doing only debuyer and BLC, a black level calibration. On the right side, you can see a result of the working output of the ISP. So you see it's really big difference because ISP can do white balancing, improve the dynamic range, and yeah, it's definitely there is a difference. If we're talking about TI ISP, it's quite advanced. It has all necessary blocks to process your video inputs. It has enough performance. It's in my view, that's about 16 megapixel for sure you can process. I think it's much higher. Depends on, of course, on the pixel rate. There is some limitation on performance, but I think, yeah, we need to calculate the right performance of the sensor and if it's enough performance of the ISP. But if we look on ISP, we have, if we check the possibility of that TI block, we have all necessary blocks to eliminate impact of the lens, as we discussed before, like defect pixel correction, lens shading, do some statistics for the next block, for the noise filter, for tone mapping, for brightness contrast enhancement, and for debuyer and gamma correction. And you see also you can do chromatic aberration correction. So basically, that you will see that it removes all the these impacts from the lens issues and so on. In software, how it's done today, if you look on Toradex software, there is a standard plugin, number of plugins for the guest streamer, and once plugin is used for ISP, like the first plugin is used for ISP block, the second one for lens correction, and then for converting output. So you can select which one of the you need, like U format or RGB or whatever. So MSC block allows you to change the output format. And every block has a specific parameters, so you can apply per camera or per stream different types of parameters. ISP calibration allows us to, you see, improve the colors of the image and quality of the picture. So you at the beginning, when on the level of the black level correction, you see it's a bit blurry, and it improves by changing black level correction. Then on the white balance calibration, there is 4 ways or even more, depends on the light source. There is a number of calibration steps using different lights, light spectrum, light temperature. And then we have a white balance tuning that allows us to match, to do the matching of the colors based on the lighting conditions, and then we do color map tuning to be sure that we see really nice and 100% correct colors according what we can measure with equipment. We do in our company, we do ISP calibration, use special equipment. We have a tool for that, and we do for this for TI platform. So if you need calibration, we can do for that for you. If you're talking about specific Aquila and Toradex platform software part, I will show you example of really demo how it works and a load of the processor during this demo. So this is a part of the standard demo that provides by Toradex and TI. So running this demo of SSD mobile net on only a single video, so you can see it's only about 4.2% of the CPU have AI engine load and 30 FPS, and there is no frame drop or something. And this is an object detection demo. Then the demo is object segmentation is a bit more heavy, high resolution of high resolution of the picture arrives to the AI block. a bit higher engine load and a bit more MPU, but still manageable with the 30 FPS. Another interesting demo when we have 12 video streams in the same time. So you can see we have some load on AI engine, but it's not fully loaded. If we look on the memory bandwidth, it's completely not loaded at all, because memory bandwidth depends on a physical memory connection. It's about 128 megabit connection of the DDR4, so there's enough bandwidth. But the internal bandwidth of the processor is enough to process even 12 video streams, and we have a 25 watts in total while kind of streaming video. So basically, it's about 2.5 watts per video stream. I also did a demo with barcode scanning. So run a barcode algorithm on a processor, not on DSP, not on a OpenCL or other, just running on Neon optimized barcode scanning codes, and I got 3 milliseconds with 8 parallel threads, 8 parallel barcode scanning applications running, and I got, of course, 100% CPU load, but at the same time, all of them report about 3 milliseconds per scanning. Then typical application that you can run on a TI platform. So it's up to 8 cameras or 12 cameras connected to the ISP block. Like here on this demo, it's 8 cameras with full HD resolution. So all of them can be processed through the whole pipeline, including AI engine, so object detection or segmentation, whatever. And also you can record the video. So we have a codecs to store encoded video and stream them through the network. In our site, we are now designing, and we're going to produce our Aqua Edge platform based on Aquila IM69M module, and we will have a number of interfaces, allow our customers to connect different peripheral blocks, and this unit will serve also 8 cameras in parallel. For typical applications we want to match and we see potential is people counting, barcode on QR scanning on factory automation, using also AI for post-processing, automotive, and number of other applications where with a lot of big demand is coming, like good sorting, false factory alarm, scene detection, process tracking, and so on, mobile robotics, and so on and so on. Yeah, so I would like to thank you for patience, and will give my word back to Carlos. Carlos, your floor is yours.
Thank you, Artyom, so much. That was extremely useful, informative, educational. So thank you so much. I think we learned a lot from you. So I'll just quickly go through a little bit of content about Toradex itself. So we'll just provide the last couple of bullet points, introduction to Toradex and its vision ecosystem, and then we'll jump right away into the Q&A. So as most of you probably already know, Toradex is a leader in embedded computing. We focus on making embedded computer easy to use, and we do so by providing highly reliable ARM board SOMs, including production software. So we strive to offer the lowest cost of ownership, and we do that not only just by focusing on the SOM, but also on the development effort, the time to market, so essentially making it very easy to get onboarded and to get all the different peripherals and all the software integrated, and obviously long-term maintenance and availability. So the last one, which I think is the reason why many people use and choose Toradex, is because of the industry-leading support. So we have a very active community, and also a very broad and deep developer site with a lot of resources. But obviously, many people choose Toradex because of the software, and a big part of that is Torizon. So Torizon is an easy-to-use industrial Linux platform. It offers the embedded Linux operating system, but also a cloud platform that is simplifying a lot the development and the operation of an IoT system, and offers, for example, device monitoring, remote access and updates, fleet management, integrated security features. So it's actually a very comprehensive platform. We use containers as well for application development. So this is definitely one of the reasons why people decide to use Toradex. But we are mostly known because of our system of modules. So here you can have a bit of an overview of all the different families. So as you probably know, the SOMs are pin compatible within the family, and within actually these families there's a lot of variety. So you can go from very high performance and to very low performance, so actually lower price. So you actually have the whole range of possibilities as we actually outline over here. So the Colibri family is our oldest family. But we go all the way up to the Aquila family, which we just launched last year. And the main module that we launched on this family was actually the AM69, the Aquila AM69, which Artyom was actually talking about. So that is one of the main platforms, especially for computer vision solutions. We also have a couple of new SOMs on the IMX95 platform, both on the Aquila family and the Verdin family. We have recently also launched the Smart family for more like a standard form factors. So overall, you know, a wide diversity and variety of different options. When it comes to computer vision and the camera ecosystem in particular, just wanted to outline a little bit how we're doing this. So we don't manufacture ourselves cameras. We work with third-party camera providers. The way we do it is it's a bit of like a you know, ladder, if you want to look at it. So we have evaluation cameras ready to go. So these are actually pretty much plug and play. That's the goal, that you can get them from our website, and you can use them for testing and for quick development and quick demoing purposes. So if you want to build a prototype, you can just get one of these cameras and it should just work pretty much across our portfolio. But we also work with trusted partners. We test the cameras. There's a lot of testing going on to be able to essentially to be a proven partner. And we have a bunch of different solutions, industrial level solutions that we have tested with our partners. But we also have a very rich peripheral database that includes compatible cameras. And again, we add them to this peripheral database after a lot of testing to make sure that they work. Although we don't really manufacture these cameras, they are always actually tested, and we try to keep it updated as much as possible. So that's in a nutshell how we try to keep our camera ecosystem alive and rich and basically up to date. So with that, I wanted to actually move to the Q&A session. I've seen that there were a lot of questions actually from the audience. So maybe I'll just go and start with a few of the questions, and some of them may be for me, some of them may actually be for Bruno, for Art. So the first one that I see here is, what hardware would you recommend for a computer vision project that requires machine learning and AI capabilities? So maybe I can take this one. You know, Art, you know, feel free to jump in if you want to add anything. I mean, obviously, the one hardware that we would recommend is the one that we were talking about. I think it's the M69. The Aquila M69 seems to be a really good, a very appropriate solution because of the multi-camera capabilities. So essentially, with that, you can use up to 12 cameras. So it is definitely a very good solution if you are looking at computer vision. On the Toradex ecosystem, we also have a couple of other options that can probably be a very good option. One is the Verdin IMX Plus. So the IMX 8M Plus is a very good option, maybe a lower price, but also with a neural processing unit, and also a lot of camera compatibility, and obviously the IMX95, which is high performance in terms of NPU and also camera support. But yeah, Art, I don't know if you want to actually say anything about the hardware that you would recommend for a computer vision project. I guess it will very much depend on what project and what is that about, right?
Yes, thanks. I would like to just accomplish one thing. Need to first check what kind of models supported by your hardware and software, because models are different and tensors are different and the structure of the models are different. So when you selecting right platform, also be careful with selecting the model, what kind of model you do and performance you need, of course. So might be, for example, IMX 8 and Plus is enough. Why you need an Aquila or vice versa? If you need a high performance, welcome to Aquila world.
Yeah, exactly. I think that's a very good point. Is that there's no two projects that are the same. So we'll need to actually understand more the needs and the use case. Thank you. All right, next question is what cameras are available off the shelf from Toradex? So yeah, I can take this one. So maybe actually just quickly, we go back to the, I think it's the previous slides. I think we have it here. So what is off the shelf? So is the two first bullets here, the first two circles. So it's the evaluation cameras. These are actually available from our web shop, and it should be actually very simple just to connect them and get them going. So we have a camera from Arducam, the OV5640, and then also from Nikon Systems, we have a camera available. And then the other one that is quite easy to install and get going is the CMOS FSM Go. That's also a very good camera. For any other cameras that you probably need to do a bit more investigation, more integration, but we can help you with that.
From my side, I can add we have already available cameras that we can connect to Aquila boards. We do calibration, but we have already a GMSL cameras, very small like this. Small, tiny, and this we have 23 types of sensors. So you can select it's a color sensor, monochrome sensors, VGA adds up to 20 megapixel, and it's a GMSL 2 cameras. It's IP67, 69 protected. So no, just send me a message and I will help you to select the right one.
Good, thanks, Art. That was great. All right, another question is, what is the maximum length of the GMSL connection? I think, Art, you mentioned that. I think it's about 20, is it 20 centimeters, or how long is
20
that?
meters, yeah.
20 meters, okay, 20 meters.
Let me say in this way. So we have today 3 types of GMSL, 1, 2, 3. I think on the 3 even longer, it's up to 20. GMSL, it's 15.
Got it, okay, thanks. All right, next one. So you mentioned the Aquila M69. What is the maximum number of MIPI cameras that it supports? So I think it's 3 quad lane MIPI CSI 2.
Yeah, I can answer that, Carlos, if you want. So
up to 12, right?
Mm-hmm. So Aquila supports. I didn't speak about that, but it supports virtual channels on MIPI. So we can have virtual channels. So I think we have 8 for sure, but I need to check. Maybe we can have 12. No.
Got it. Okay, thanks. This one is also quite interesting. Is how does the M69 compare to NVIDIA Jetson? So
NVIDIA Jetson is much more powerful in terms of Jetson. Which one Jetson? There is a number of Jetsons, AJX or Nano. That's a thing. But we also need to compare power consumption. Aquila is much lower in terms of power consumption if you compare.
Yeah. I mean, that is a very good point, because there are many different options within the Jetson family.
And the price difference, I think.
Price, yeah. Probably the Orin series is kind of the more similar one. I mean, the price obviously is I think the price quality or the price feature comparison is quite different, and also the NPU. So I think with the Orin you can get to almost like 300 tops, but I think you're going for quality of the camera and the kind of like a versatility of the software stack. Maybe actually you maybe
exactly.
the DI ecosystem is a bit more versatile.
I will say in this way that NVIDIA versus Akula, I see a benefit of Akula only in image vision pipeline. Why? Because owning costs of NVIDIA software is much higher. You need to have a partner who do the calibration for you, while all source code of gas streamer plugins is available. There is no hiding blocks, so you can if you want, you can play with the calibration data, so you can tune by yourself video pipeline and so on. On MTI, everything is open source. Almost everything is open source.
And I think it's also worth mentioning that with an industrial temperature range, the options for Jetsons are much smaller and much more expensive. So with the TI-M69, you get that industrial temperature range at lower price, lower performance, and lower power consumption.
Good. Thank you so much, Bruno, for jumping in, and Artyom for all your content in answers to the questions. So I don't really see any additional question right now. But guys, if anybody in this webinar has any questions after the session, just feel free to send them over to us. We'll be following up in a few days with the presentation, and the recording will be available on demand as well. But with that, I would just I would like to thank Artyom actually for your time and for all the work that you put on this. And I hope that it was actually a productive and a useful session for everybody. Thank you so much.
Thank you for hosting. Thank you for visiting.